Right, guys, let's come. Today we are looking at vectors. Vectors, maybe you can look at them as some mathematical entities of some physical entities. I think the vectors we find them in physics, we find them in mathematics, vectors. But the most interesting thing, what is a vector? Or maybe what characterizes a vector? But before we talk about the vector, let's be aware that we can talk of what we call vector quantity, the vector quantity. We can also talk of what we call a scalar quantity. I think something which is almost obvious to all of us is a scalar quantity. What is a scalar quantity? A scalar quantity is something like, we can say, speed. Speed, mass, maybe time also. So, because when I'm talking about this kind of quantities, speed, I can just say my mass is 50 kg. That's scalar quantity. I can say the speed of a car or an aeroplane is 600 kilometers per hour. Some of these things, if we add something else, you might find that we then talk of a vector. Altogether. Now, I can say, maybe let's start from the speed and say a car is traveling at 60 kilometers per hour due east. That is now not a scalar quantity, that's a vector quantity. And then I ask the question, what characterizes a vector quantity? A vector quantity, when we said 600 kilometers per hour here, we just gave the magnitude of that speed. We just gave the magnitude of the mass. But now when we're coming here, we're giving both the magnitude, which is 60 kilometers, and direction. So a vector is not a vector without direction. A vector is a pair of things. We must have magnitude and direction. Now, how do you represent vectors? There are many ways you can represent vectors. One way is this one. You can have a segment like that. Oh, what's happening here? Sorry, you can take a segment and orient it to the segment with a direction. So what happens there? It shows us in which direction, and then the length of the segment, let's say from there to there. This could be length in any units of measure, maybe centimeters or kilometers. That is what we call from there to there. That is what we call the magnitude. The magnitude of the vector. Now is the length of the vector. And then the direction is given by the arrow. So I think this is the simplest way of representing vectors. Representing as what we call directed segments. Directed segments. Now, once we have represented the vectors this way, the question comes naturally that, okay, if we were looking at directed segments like this, and we were looking at them at vectors, then the question is, as mathematical entities, what can we do with vectors? And in this case, if this is a vector, I can name the vector using small letters, like I can say, this is a vector A. You will find that some people have got a tendency of putting a kind of a segment under A, but I'm more used to writing this A with an arrow at the top altogether. So, but don't confuse, get confused when you find some other kind of notation in the thing, the vector. And some people just make the letter A bold somehow, and just say that's a vector altogether. But let's use this thing of arrow, and that's the thing. Okay, let me see if I can get something interesting here. Let me go to the, let's see. Again, we're still dealing with vectors. No, I don't want that now. I don't want that now. Let's do this. Let's do this. Let's have an arrow like we had before. I now want to operations with vectors. Let's just say the operations. Operations is 1p, ne? Operations 1p, is it? Okay. I don't know. I wanted to put double p there. I don't know why. Operations with vectors. Now we've got these things we call vectors, directed segments. We've got directed segments. So this vector, I can call it A, and this vector is B. The thing is, if I got two vectors like that, and I say I want to add them, how do I add them? Unfortunately, I don't have this. I cannot use a protractor or a set square. I will demonstrate that thing on the board altogether. But essentially, what happens is, you know, you can transport a segment from one place to another, and then using a protractor and the ruler. Not a protractor, a set square and the ruler. So essentially, what happens if you are going to add two vectors like this? This is what to do. I'm going to demonstrate this thing on the board later. What you do is you sort of create, now to transport that tail to the head of this one, and then you draw a parallel to this line which comes around here at the head. Then what you do with your set square, you put your set square along this line, then you transport that segment to somewhere here. Then you've got that segment transported to somewhere there, parallel. What you end up with here, with these red two lines and these two, they form a parallelogram. Then if this is P, then because a vector is that movement from the tail to the head, we call this the head and that the tail, isn't it? So now, if now we say, if you put the vectors this way, notice that you've got another vector which can come from here to there. And this is the vector we're going to call A plus B. That is what we can call the resulting vector. All together, guys. Any question at that point? What can I say? Nothing. Okay, so what we're doing there, guys, we are adding two vectors. All together. Yeah. You know, this thing is a codec function of getting arrows here, but I don't know what happens now. I can't get it. I don't know what happens. All right. So let's talk about subtraction. Let's talk about subtraction. So simple summarizing: if you're adding two vectors in this fashion using directed segments, you just to put them. If you say A plus B, like you see on here, the tail of B must be at the head of A. Altogether. Then you just take the tail of A to the head of B. Then you've got the sum of A and the B, and call that A plus B. Is that right? Okay. Now let's say now we've got C. Let's say we've got C. Let's say we've got C. Let me try this one. And then let's say you've got C there. That's a vector C. And then let's write a C. And let's say I've got D. Don't go on that one. I want this one. I've got D there. And that is D. And we're talking about subtraction now, isn't it? Let's say I need C, vector C minus vector D. Now together, C minus vector D. This is what we're going to do. Normally I wrote them, put them this way because I want it's more convenient with me to say. What we're going to do, something similar but slightly different. You're going to transport this D in such a way that the tail of D is going to come here. Now you draw the parallels here. Then the next thing is to fit your C, your D there between those parallels. It doesn't look parallel. I don't want it to look more parallel than that. You go better. Now this is D. What happens here? A vector, actually a vector, when I'm looking at D here, is just the representative of a vector D. Now all the parallels to D between these two red lines are vector D. So it's represented there, it's represented there, and all there in between. So that's what you must understand. So I can, any vector given anywhere, I can position it at any position of the plane just by transporting it. So now this is D. Now where is vector C minus D? Then vector C minus D will start from the head of, as long as I'm subtracting D, it will start from the head of D. It will go from the head of D and the go and the meet C there at the head. Then what I've got here, this is a vector, the arrow there. Then this is C minus D. That's the vector C minus D. Is that clear, guys? By that time, you've got a ruler and a set square. You just put your set square against D, draw parallels, then you transport it between parallels, you've got D, then you join that one. All together? Okay. Yes? Yes? What is it? I'm not sure what is it entail. Can you show me that quick paper? Yeah. This is addition. When I'm saying A plus B, I take the tail of B to the head of C. Then the resulting vector starts from the tail of A to the head of. This is subtraction. It's something else. Can't be the same. Yeah. So this is subtraction. Now the tails share a common starting point. Then now there are two vectors we're going to have here. Now, if I've got a vector A, there's always another vector I can call minus A. These two vectors, they are exactly of the same magnitude. What is different? The orientation. If A is going that way, minus A with exactly the same length will go that way. You understand what I'm saying? Okay. So now, in this case here, I could have taken D minus C. From what I explained, you must be able to determine what is D minus C. Actually, you can see that if I put a minus before these two vectors, D, what's going to happen? I'm going to have that one, isn't it? So which means this vector is the opposite of that one. Are we together? So different orientation. That is vectors as segments. Also, we can multiply vectors by numbers, like scalar multiplication. We talked about multiplying matrices by scalar. We can also have a number here, lambda. Let's say lambda is equal to 2. And I've got vector A here. Let's say I've got vector A here. What is vector 2A? Vector 2A is just taking this A twice. In other words, I'm adding A plus A. But obviously, if you add A plus A 2 times, you're multiplying by 2, isn't it? So that's what we call scalar multiplication there. So in general, if you've got A, you can also get lambda A. And this lambda can be greater than 1, can be greater than 1, or can be, let's say, the absolute value of lambda. Maybe let me talk about the absolute value of lambda. The absolute value of lambda can be greater than 1. So lambda itself can be negative or positive. So if lambda is negative, the vector will change orientation. If A is looking in that direction and the lambda is negative, lambda A is going to look in the opposite direction because it changes orientation. Am I making myself clear there? Okay. But again, if absolute value of lambda is greater than 1, whether negative or positive, which means the resulting vector is going to have a bigger magnitude than the original one. But if it's less than 1, let's say lambda is between 0, the absolute value of lambda is between 0 and 1, then, like, maybe let's take half A. If I take half A, what's going to happen? The length of A is going to be reduced. Is that right? Now I've got A here. Then if I take half A, that vector, then the magnitude of this A will go up to halfway there. Then there I've got what I can call half A. I think that is clear. You understood? Yeah. But the problem is, working with vectors this way, I think is a bit challenging. It's quite challenging altogether. But what comes to our rescue when we are working with vectors is the Cartesian system of coordinates. You know about this, isn't it? The Cartesian system of coordinates. Now, if I draw a vector, like I can draw a vector this way and put an arrow there, and I can draw a vector this way and put an arrow there. Now, I cannot just say this vector A and stop there, and this is vector B and stop there. Now, I can put numbers to this vector if I want. So, like, let me first of all do this. If I put a vector like this, I think you can see that as I'm moving from this, let's say this line is perpendicular here, and I'm moving up to there. There are two distances which are changing there. I'm going up somehow. Here I'm displacing going up, but at the same time I'm displacing going horizontal. When I'm starting at this point here, I'm at this level, I'm here. But when I'm here, I'm at that level, vertically I'm at that level, but horizontally I'm that way. Isn't it? So which means a vector coming up this way can always be represented by kind of two movements. The horizontal movement and a vertical movement. And then if you look, that vector is actually the sum of this vector which is horizontal and that vector which is what? Vertical. This is what we call decomposition of a vector into a horizontal and vertical component. So now this is the vector, this becomes its component. Now when you come to a system of coordinates like this, I can now say vector B, once I put a system of, remember the plane I was using before, it was just a blank plane, no numbers, nothing. Now once we've got a system of coordinates, Cartesian coordinates, thanks to that, now I can say vector B can be represented by 1, 2, 3, 4, 5 horizontal movement units, 5 units on the horizontal and 1 on the vertical, then that. Then now the vectors become that. Now the vectors can be represented in what? In using two numbers. And I think from what I've said here, one number is the horizontal component and the other one is the vertical. This is how we represent them. Put them first x, then y. How do that? Then what is A? What is A? Can you tell me what is A? A, using those coordinates now, A is what? 3, 3. All together. Now, the other thing now, you can now even add A plus B using vector, using this kind of representation. But once you use this kind of representation, again, once more here, we're coming back to matrices. What are these? Column matrices. You see that? They are vectors in essence here, but they are represented as what? As column matrices. Now when we're talking about adding them, we're talking about adding column matrices. Is anyone doesn't know how to add matrices? Is anyone doesn't know? Hello? Who doesn't know how to add matrices? That's it. Okay, so everybody knows how to add matrices. So if the end test what you say now, you will say 3, comma, bracket plus 5, 1. If you take your graph paper and do exactly what I've done here, take your set square, do what I said you must do with the set square. What I showed you can do with the set square. Then check these values you're going to get here. You're going to get exactly the same thing. If you don't, then there's something wrong with your scale. So it's 5 plus what? That will be 8. And what? 3 plus that will be 4. Then that's a new vector. But here, I put the vectors, all of them, to start at the origin. That doesn't mean that they should always start at the origin. I can give you a vector here like this. You must be able to tell me what is this vector. Can you give me the coordinates for this vector? Let's say this vector is C. Let's give me the matrix which represents that vector. Can you check it? Right. What is it? I said, give me this vector. So we said, we're going to name it C. What is it? C equals to? C is equal to? Can I have one person, please? One who wants to tell me the right answer? Yes? 2, 1. What are we talking about? We're talking about this horizontal displacement here of 2 and that one of 1. But if I come and put this vector here, let me put it here in another color so that you can see it clearly. If I come and put it here, that is same vector C. This is vector C. That is C and that is C. Then this, in this position, red, we say the vector is in its standard position. What does it mean to say a vector is in its standard position? It means that the origin, its tail, is at the origin of the system of coordinates. All together. Then what is interesting also, once you've got vectors represented this way, is that we can be able to calculate the magnitude of vector. This is how we represent the magnitude of the vector. That's what we do. We put it as an absolute value of the vector, but we call that the magnitude of the vector. You can even say the absolute value of the vector. I think there's something which is offering itself there. If you look at B, you look at A, you look at C, there is something which is offering us. Remember, the magnitude is the length of the vector. Remember, I said the vector is given by the magnitude and the direction. The direction you can see from the arrow, but there's something we don't have. It's the magnitude. How do you think we can calculate it from there, from what you see on the board there? What can we use? What can we exploit? Something we know which you can exploit. Come again? I can't hear what they said. Pythagoras. So Pythagoras, and this case here, we're talking about that the head for C there is represented by coordinates x, y. Now I'm taking this as a point, the head of the vector is represented by x, y. But now if I want the distance of that point from the origin, I can use Pythagoras by taking x as the adjacent, this side, and that one as the opposite to that angle. Then what I can say now here, actually what you call the R when we're talking about the trigonometry, then here we're calling it modulus of the vector or absolute value of the vector. This is called modulus of the vector or absolute value of the vector, is same, or magnitude. So that R which is called there was calculated by x squared plus y squared. So a vector having a vector also, it is both x and y. That's exactly what we're going to do. So the up modulus of C is going to be 2 squared plus 1 squared, which is going to give us 4, 5. That's square root of 5. Units, whatever units you are using there. You could be using centimeters, you could be using normally standard international units for length is what? Meters. So then you can use fractions of meters there, like centimeters or millimeters and so on. All together. Okay. So that's one thing. Then in terms of direction, let's suppose this was not drawn, you cannot see the direction. You can also, direction you can give it in terms of an angle. All together. You can take it into an angle. Now, what angle are we talking about here? We're talking about this angle. This theta here is the one which gives the direction of that vector. That angle there is one which gives the direction of the vector. That angle there is the one which gives the direction of that vector. So if you check this thing carefully, you will see that our trigonometry, our Pythagoras and everything, they're coming back here. You see that? So now to get that angle, given this situation that now you will put a vertical component, a horizontal component, it actually creates you what? A right angle triangle. So then, which means we can actually exploit that right angle trigonometry to get this angle. So in this case now, theta will be the second function tan of y over x. Then when you do that, then you get the direction in degrees or radians, whichever units of angles you are using. So I think you appreciate what's happening here. Once you've got a system of coordinates, you can represent a vector, you can transport a vector to standard position, you can do whatever. You can actually calculate the length of the vector without having a ruler. You can actually calculate just with the calculator and the coordinate and the common calculator, you can get that the angle which is made by the vector. Is that clear? So you get it via this formula. So now we've got the absolute value, which you can still call R, is given by a square root of x squared plus y squared. And then this one is the direction and this is magnitude. Let's say the angle gives us the direction by that formula. And in this formula, it actually gives us what we call the modulus or the magnitude of the vector or the length of the vector. So don't get confused when you get all those names they used. Again here, I think you are able to see that if you are saying sine of theta is equals to x, sorry, is equal to what? Y, ne? Is equals to y over r, which is the modulus of the vector. I think you can see that your vertical component y is still given by r sine theta. That's a formula for getting that. Are we together? So then you can also from there get that your horizontal component of x is given by r cosine theta. Are we together, guys? Okay. Okay, guys, I think up to there, that's enough introduction. We're going to carry on from there Monday. And then I would like to say thank you for listening. I hope your experience was good today. But if it was negative, sorry, it wasn't my intention. Bye-bye.